Yeah, thanks for the confirmation, Pallavi madam. So, as you can see in my first slide, I have mentioned along with me, Surendra Kumar Saini is my present PhD student, and uh, Poonam Devi has graduated a couple of years back, and I've also mentioned Shilpa Das. She did her MTech at MNIT Jaipur, and she is presently pursuing her PhD at IIT Delhi. So these slides are actually a culmination of all of their work. So what I would be discussing is indoor optical wireless technologies. And this technology is not directly related with 5G, but these technologies may be a part in future wireless systems. Uh, as you're all aware that 5G is trying to, not just 5G, but wireless communication in general is trying to enhance the data rates and reduce the latency. This is the main focus. So if we talk about 4G communication, the data rates that we were supposed to have was of the order of some 100 Mbps or so. But if we look at the practically implemented technologies, then we hardly get 20 to 40 Mbps in 4G. When we are moving towards 5G, the data rates have indeed increased quite a bit, but it was targeted that the data rate should be of the order of around 1 Gbps or so in 5G, but that is presently not achieved when you look at what has been deployed. So people are able to get 500, 700 Mbps of download speeds, uh, but that is one aspect of the enhanced technologies in the wireless domain. So uh, when I'm talking about wireless communications, we are talking about mobile communication. With reference to this mobile communication, I mentioned about these data rates of 20 to 40 Mbps in the 4G domain and about 500 to 700 Mbps in the 5G domain. Uh, if we uh, discuss about similar technology, which is Wi-Fi, but of course this is a wireless local area network, so this obviously has range limitations. This works only within a smaller range. So within this smaller range, in a wireless LAN scenario, it is possible to get higher data rates. So depending on the generation of the wireless access point which is deployed and the background switches which have been deployed, the access speed can vary. So if there are sufficiently high-end switches and wireless access points, then the data rates can easily cross even 1 Gbps. But of course, as of now, we do not have uh, user equipments which are able to download at such high rates, wireless user devices, because the mobile devices that we are using, these are not even using uh, the Wi-Fi 6. In wireless technologies, we have in wireless LAN technologies, there are different generations. About I'm not I'm not able to recall the exact all the variations, But all these variations come under the 802 the IEEE standards of 802.11. I think it's A, B, G, N, and A, B, G, N are the different Wi-Fi standards, and this N I think refers to the Wi-Fi 5, what it is called, and the sixth generation of Wi-Fi refers to AX series, IEEE 802.11 AX. So with that, using MIMO, uh, Wi-Fi access points have been able to deliver quite high data rates of even, I think it goes up to around 15 Gbps per access point. So a single wireless access point can deliver about 15 Gbps of data uh, to one or multiple users. But of course, that would mean a user, if it is a single user which is connected and the user does not have a compatible Wi-Fi 6 technology on the mobile, then it will only be able to, the user will only be able to experience the Wi-Fi 5 technology. Whatever is available on the mobile device, that would be used. So that is one aspect, wherein if newer mobile devices are coming into the picture, then it's possible to have even 1 Gbps of data rate transfers. But getting such type of data rate transfers in mobile communication through the 5G communication, that is still challenging, considering all the aspects of mobile communication. Some aspects of wireless connectivity can be through optical wireless technologies, which was discussed by Professor Prashant Sahu from IIT Bhubaneswar in one of the previous sessions. And he discussed about wireless point-to-point links, which can be outdoor. So today what I'll be discussing about is not outdoor, I'll be discussing about what we can do indoor. So if you're aware of optical communications basically need means the fundamental way of using optical communications so far has been through optical fibers. And with the use of optical fibers, the data rates that companies have achieved so far using a single fiber has gone up to 800 Gbps. So data rates of 800 Gbps are very much possible right now using a single fiber, and this is available in the market. Of course, these high data rates are not commonly used, and hence you won't be able to find it in the market just like apples or oranges. So, but if you are placing an order, then you can have it delivered in your home also. So there are companies which are making optical communication links possible of the order of 800 Gbps using a single fiber, and that does not use very complex optical circuitry. So mostly if we think about 800 Gbps in the wireless scenario, even that is a possibility. So this is what I'll be thinking, I'll be discussing about how we can try to implement such a thing. So this is the overview of what I'll be touching upon today. I'll be introducing what indoor optical wireless communication is. Actually, if you compare with mobile communication, optical communication has or optical wireless communication has one serious disadvantage, and that is line of sight communication. So optical wireless communication needs line of sight communication. Without line of sight communication, optical wireless communication is not able to provide high data rates. So that is one major disadvantage offered by optical wireless communications. So and because of this, there are many alternative technologies which are being proposed, in which the advantages of the RF technologies and the optical technologies can be clubbed together, and people are working on hybrid systems also. I believe even Professor Prashant also discussed about that. So indoor optical wireless communication has the ability to deliver high data rates of the order of even 800 Gbps, point to point, or could be point to multi-point, depending on how it is deployed. So that could be that is actually, I think, an unlikely scenario in 5G communications, but this may be used in future generations like 6G or 7G. So I'll be introducing how indoor optical wireless communication or what it is, and then what are the technologies which have been developed so far, what are the advantages, the challenges, and some recent advances, and some of the applications and use cases where the optical wireless communications have been discussed. And I'll also be discussing about some emerging trends and future directions. So coming to the introduction, this is the OWC refers to the optical wireless communication, and it uses optical signals. So these optical signals can be infrared, can be visible or ultraviolet, and but most of the research articles that you would see, those use the visible wavelengths for transmission of data, and few also mention about infrared wavelengths. So the sub-technologies which are already, there's a lot of research which is already going on, that is based on VLC, which stands for visible light communication, and the wavelength that this communication technology uses, that is from 400 to 800 nanometers. And there's also another technology which is Li-Fi. Just as we have Wi-Fi, the term Li-Fi has also been coined relating to light fidelity. And there is a standard for this Li-Fi, and that is 802.15.7 by IEEE. And even IR-based optical wireless communication has also been discussed in some of the literature, and these use 850 nanometers or 1550 nanometer lasers, or even, of course, it's possible to have any other laser wavelengths also. So coming to the scope and importance, if we need ultra dense networks where we have multiple devices which need to connect to the network, and they're all at a very close proximity, ultra dense networks would probably refer to something like hundreds of devices or so. So if each of these hundreds of devices would need connectivity, then the data rate for each of these uh, nodes would fall down if the access point uh, could be a mobile tower or a wireless access point, wireless LAN based access point, the data rates would fall. So in such ultra dense networks, uh, which is a likely scenario for 6G, this indoor optical wireless communication is a likely candidate. So, as I mentioned about the 800 Gbps of data rate transmission speeds, these are already available through a fiber. So, with some modifications, it might be possible to have such high uh, data rate connectivity using uh, the similar technology as for the optical communication in an indoor scenario for optical wireless communication. So another important advantage offered by this optical wireless communication is there are many areas where electromagnetic interference is undesirable, like in hospitals or in aviation. And so in hospitals or in the aviation sector, uh, most of the equipment works on certain frequencies, and hence it is not desirable to use Wi-Fi or wireless access points or mobile signals. So in such zones, the indoor optical wireless communication setup can be useful. And IoT backhaul can also be a useful scenario depending on where the things are. If it is indoor, it can be indoor, or if the Internet of Things are connected in the outdoor, then FSO is a likely candidate to connect the IoT nodes. So on the left, we have the connection from where the metro network or the core network that refers to the service provider, and the service providers usually connect through access networks to different locations. So this connectivity is presently, I believe you're all aware of the FTTH revolution that is going on in our country. In most of the urban areas, almost every home is connected with a fiber. And this fiber connectivity is able to provide decent data rates. Of course, the reliability depends on the service provider. The the connectivity is decent, the data rates are decent, and the prices are low. That is the main advantage why this FTTH is exploding across the globe. The main reason why the prices are low in FTTH is the power consumption. The power consumption of these fiber-based components, these are much less compared to the power which is consumed by the traditional wireless equipment, that is the radios used by mobile communication equipment, and the wireless LAN or wireless access points which are being used. Even these use quite a huge amount of power to deliver data to the user equipment. or mobile phones. So the fiber has been able to reach up to our homes, and the technology which is behind this expansion is FTTH, also known as fiber to the home. So this technology was proposed way back, probably 20 or 30 years back, and we are seeing this expansion in the last 5 to 10 years. So before 10 years, the fiber used to be quite expensive, and hence the deployment costs were also quite higher. But the present day, the fiber costs are much less compared to the cost of copper cabling. So hence the FTTH deployments are quite high, and people are using the fiber-based optical network terminals in homes to access the internet. So in this, if you see, within a home, there is what I have mentioned here as a home gateway. So once we have access to the home gateway, within the home, the network can be distributed through Wi-Fi or through optical wireless communication or through multimode fibers or plastic optical fibers, or even it could be the standard single mode fiber. So all of these technologies or components can be used to get the end user connectivity to the mobile or laptop, whatever is being used. So if I am talking about the indoor optical wireless communication systems, then there's quite a complexity which can arise in the system. See, the data that we have, that could be electrical, but if it is on an optical fiber, then it is in the optical domain. So assuming that we have electrical data, then we need to convert those into into the optical domain for transmission through the optical carrier. So usually when we talk about visible light communication or Li-Fi, this electrical to optical conversion is usually done through LEDs or light emitting diodes, because that's what we are using, or we have started to use in the last few years. The fluorescent lamps are being replaced by LEDs, and we researchers of optical communication or optical wireless communication are trying to embed data through these LEDs and transfer it to the user equipment. So this is the optical assembly which needs to be put with lighting equipment. Could be an LED or it could be an LED assembly, which would also need some additional circuitry to combine the data with the light. And so if you can see here, then in order to provide connectivity, you should be having line of sight signals. So if there is any object which is within this line of sight, then the signal would be lost. The receiver will not be able to receive whatever is transmitted by the transmitter. So this is one major disadvantage of this technology. But once if there is line of sight signals, it can be a very good high data rate connectivity. But along with that, there would be neighboring problems. It's possible that some shadowing object would cause a reflection of the same signal. And as you might be aware of the problem of multipath fading in wireless communications. Here also multipath signals would cause interference at the receiver. So this is one aspect of the problem that can come. Another aspect of the problem would be turbulence because of fans. This the speed of the wind that can actually of course the wind this these lines actually refer to wind, right? So the wind would actually not be able to interfere with light as it is per se, but the way it can interfere is it has the capability to shake the receiver. So if the receiver is not stable, then we will have some disturbance. So that's how even the fans could be a problem for uh, optical wireless communication links. And if we have neighboring lamps or LEDs, it's highly likely. If you can take a look at my video, uh, you can see multiple lights above me, right? I'm sorry, I got disconnected. So I was talking about having multiple lights in the background. So when we have multiple lights, then the receiver could be getting the neighboring lamps light. That would be also noise for the receiver, which is trying to receive signal from the main source. So this is how an optical wireless communication system would need to function along with all these problems. And there are visible light communication links and there are Li-Fi systems, and these are two very similar technologies which are being explored. So researchers, there's a lot of research articles in which you'll see that people are proposing Li-Fi systems and there are people who are proposing visible light communication systems. So if you look at the two figures here, it's almost the same. The visible light communication uses LED lamps and even the Li-Fi systems use LED lamps. So mostly it is more or less similar in nature. It's more like the nomenclature is slightly different. Here, Li-Fi does not specify what kind of light. So the wavelengths in a Li-Fi system can be much beyond the visible light. The visible light, as the name suggests, visible light has a wavelength from 400 to approx 800 nanometers, and those are the wavelengths which are used in visible light communication links. This term visible light has mainly come up because of the LED lamps which are used for illumination. And Li-Fi, this was coined by Harald Haas. So he was the pioneer who started this Li-Fi system. But this is a much more wide range of wavelengths which can be used. So these are some of the ways in which optical wireless communications in the form of visible light communication or Li-Fi could be deployed. There are some use cases or deployments of these systems in some specific environments. Of course, as of now, it is mostly research testbed kind of a scenario where these kind of systems have been deployed. So coming to the standardization, I discussed some part of this. So RF is a completely mature technology and it is quite standardized. There are several different standards. 802, as just I had mentioned a few minutes back about 802.11 A, B, G, N, AX, and AX. After AX, I think BE is the next standard, I think, which is coming up or has already come. I think that refers to Wi-Fi 7. And coming to VLC, there's also a standard by IEEE, that is 802.15.7. This had come up in 2011. And Li-Fi, the standardization is in progress. It's not completely standard, but there are study groups which are working on how this can be standardized. So if you look at the Li-Fi and VLC. So there's a very small change here. So you can say the visible light communication is a subset of Li-Fi. So here even cameras can be used to receive the signals. The modulation formats which have been proposed in these technologies are almost the same. One can use on-off keying, phase modulation, or CDMA, or orthogonal frequency division multiplexing, or color shift keying. So color shift keying is a term which has been used here, that actually is something which is similar to wavelength division multiplexing. Here colors refer to colors actually have different wavelengths. So color shift keying is almost similar to what has been achieved in optical fibers in the form of WDM or DWDM, which is referred. The full forms are wavelength division multiplexing and dense wavelength division multiplexing. So interference is an issue in all technologies. So in Li-Fi or VLC, if it is an outdoor scenario, then sun is a very big interfering signal, sunlight. And if it is indoors, then if you have windows and light is coming or sunlight is coming in, then sunlight can also be an interfering signal indoors also, or it can be the ambient light sources. Coming to the data rates, here what is shown here is based on what is actually available in references. So it is possible to go beyond these data rates, that is a possibility, but even I could not actually test such high data rates because we do not have the facilities here to test these things. We were just able to test optical wireless transfer of power. So we could not actually test the data rate that we can transfer. So using RF, the data rates that have been possible, this is based on a reference. This has been shown to be 6 Gbps, but more recent references you can get maybe even 15 or even 20 Gbps of data rate transfers. So coming to path loss, this is medium, since both the Li-Fi and the VLC is highly dependent on the line of sight. In case of line of sight, the path loss is not very high. But if a non-line of sight signal needs to be recovered, then the path loss would be very, very high. And it is very difficult to recover the signal from the non-line of sight signal. In case of the RF signals, the path loss is of course obviously high. The main limitations in case of Li-Fi and both VLC, the distance is usually not very high. If we talk about indoor VLC based or Li-Fi based systems, then the distances are usually limited to about 5 meters, which is decent looking at any indoor scenario. So for 5 meters, it is quite possible to transmit these signals considering line of sight. So if line of sight needs to be used, then the distance of transmission comes even lower. This Li-Fi or VLC, these are not suitable for outdoor scenarios, and the communication which is normally suitable for outdoor communication is FSO or free space optical communication, and that uses the uh, infrared wavelengths for communication. Uh, of course, another major disadvantage of these Li-Fi or VLC is mobility. It will be very difficult to uh, have continuous connectivity when the user equipment is moving. Of course, the main limitation of RF is increasing the data rates. That is currently quite a challenging scenario, and also the interference of multiple signals. So, some of the recent advances which people are working on are advanced modulation schemes. So people are working on orthogonal frequency division multiplexing to club multiple signals and transmit these over uh, the optical carrier. So this is a possibility, and this has also been demonstrated. But the main challenge is that this encounters is the data which needs to be transmitted, that is actually in the electrical domain, and this needs electrical to optical conversion, and that is again a very uh, not exactly a very complex process, but it's not very simple either, and that consumes uh, power, and there's also a scenario of uh, how do I put it? Uh, Speed is an issue when I am because every device or component which I insert into a system, that has an associated bandwidth, and within that bandwidth I'll be able to uh, transmit the data. So within by using this OFDM systems, people have been able to, I think people have proposed around 1 Gbps of data rates or so. So people are also trying to work with MIMO and beamforming to improve the data rate and connectivity. And hybrid, as I mentioned earlier, hybrid RF and OWC systems are also being explored. Of course, this is one scenario because for downlink of data from the roof to the user equipment in your palm or lap, you can have light. But if you want to transmit data from your phone, which is in front of your eyes, if that has to be transmitted through light, then the light which comes out from below your eye level, that is very that will cause a lot of discomfort to the eyes, and hence the uplink is usually preferable on RF. So that is how hybrid RF OWC systems are being planned. So MIMO is quite an popular technology which is being used by RF engineers, and this is also being used by optical engineers to enhance the data rates and the reliability of the connectivity. So beamforming is a technology which is being proposed so that one can have point-to-point links without wasting too much of power. If the antennas radiate in all directions, then the range of radiation, that is usually quite low, and hence if the antenna is radiating in a single uh, in a single path, then the power is quite high which is being transmitted, and the range of transmission also is quite high. So beamforming helps in increasing the range of transmission. So this is what I was talking about. The optical links are usually preferred when I'm talking about indoor optical wireless communications. The optical links are usually preferred for the downlink scenario, and the uplink scenario is considered for the RF or means through uh, mobile based antenna, something like a 5G or a 6G scenario, or it could also be a Wi-Fi based scenario. Just a minute. So this was the work which was done by my PhD scholar. We actually thought about implementing uh, this visible light communication or a Li-Fi assembly which is based on the Mach-Zehnder modulator. So this is the construction of a Mach-Zehnder modulator, and this Mach-Zehnder modulator would need input from daylight. So the entire concept is based on the solar visible light communication. So this is what we had proposed. So if we have daylight, this would contain many wavelengths. So depending on the required wavelength, we can have thin film interference filters. These are very thin layers of dielectric material. These can be used to filter out unnecessary wavelengths and transmit only the desired wavelength into these two waveguides. And these are the two input ports of the Mach-Zehnder modulator. So on one arm of the Mach-Zehnder modulator, the light would pass as it is, but on the other arm, we implemented, of course this was all simulation that we did not have actual the facility to implement or try this particular setup or for fabrication. So we simulated this Mach-Zehnder modulator in which this arm is applied with electromagnetic field. So this electromagnetic field is being fed by the data that we need to transmit. So this whole assembly based on whether we have constructive or destructive interference within this zone, the output at A2 or P2 would be based on what is the data that is being provided in these electrical contacts. So these are electrical contacts, and through these electrical contacts, electromagnetic field is induced across this waveguide. So in that way, it is possible to use light or sunlight, to be specific. Sunlight can be used for transmission of data. Of course, with the use of the thin film interference filter, it would be just one wavelength which would be used for this transmission. So another MTech scholar, Shilpa, worked on a fiber-based Li-Fi system. So we came across these network switches which use a small form factor pluggable devices. These are the modules SFP modules refers to small form factor pluggable. These are small modules which are commonly used in network switches. So in these network switches, whenever these network switches need to connect beyond 100 meters, not even 100 meters, if the connectivity is needed beyond 90 meters, then an optical fiber connectivity is necessary. Without an optical fiber connectivity, the copper-based connections, are usually not very reliable beyond 90 meters. So if I have a copper Cat6 cable which has a capability of transmitting 1 Gbps of data rates for a distance of 90 meters, if the distance increases beyond 100 meters, the data capability falls down, and the reliability also falls down quite low. And hence usually the Ethernet cables are commonly used up to a distance of 90 meters. Whenever there is a requirement to transmit any signal over 90 meters, the SFP modules are used along with fibers to transmit the data. So if you can see in this switch, the SFP modules are slightly bigger than what we have for the RJ45 connectors. And the SFP modules are inserted into these, and these are connected to fiber. The fiber can be directly plugged into these SFP modules. And from such type of network switches which have these SFP ports, we can transmit those light signals, and it's possible to amplify these and then use a beam collimator so that the light that is transmitted is not diverging, because the light which is coming out of a fiber is usually diverging. So usually when the light is diverging, the transmission distance is not very high. Hence we used a beam collimator, and using the beam collimator we have tested and we have obtained a transmission distance of about 5 meters is possible by using beam collimators. So what we actually did was, after the beam collimator, after 5 meters, we tested how much of power we are able to get back. We used an optical power meter to measure the amount of power that we get. And beyond this, what what I'm showing you here is not an actual model that we have implemented, but this is something which can be tried and is a possible scenario to have high data rate data transmission using optical fibers, and free space in an indoor scenario. So these are some more applications. Optical wireless communications are being explored even in underwater communications. Of course, the link lengths are quite small, but these are being explored. Of course, mobile front haul from a tower to the top of a building, these can be FSO links, and the backhaul could be FSO link, or more likely the backhaul is some optical fiber link which is being used. So even in data center communications, from one rack to another rack, optical fibers are always used because of the high amount of data which needs to be transferred. Of course, So OWC in optical wireless communication in all of these scenarios is being explored. None of these is has not yet been uh, completely commercialized, but people are working, people are proposing that this is possible. So I think we have another session wherein uh, we have an expert who has worked quite a lot even on inter-satellite communication using optical devices or lasers. So these are some of the applications and use cases. So people are working on quantum communications and AI and ML driven optical wireless communications. So these are all upcoming and new areas which are being explored. So even drones could be interconnected using optical links, or these can also be RF links. So depending on what is the data rate connectivity or the data rate that is needed and the latency that is needed, these could be RF signals or these could be optical wireless links or FSO links. So people are also exploring multiple other technologies to simulate dynamic channels and integrate multiple technologies. So we could be having wireless access points and we could also be having VLC access points, and users could be using Wi-Fi for uplink and VLC for downlink. So people are working on generative adversarial networks, the even the bidirectional long short-term memory, neural networks, and the leaky rectified linear unit. These are all signal processing methods or artificial intelligence methods which people are trying to put into optical communications, and people have succeeded to some extent to have some working results. So quantum key distribution is another key application that people are exploring. So this is an attempt, I think this was recently published about satellite to ground quantum key distribution. So with this, one can have secure quantum communication. That is a possibility, and this is through optical wireless communication. So these would be this is my concluding slide. It's possible that optical wireless communication could be one of the technologies which is being used in 6G or 7G communications. And as I mentioned about the different technologies, it could be Li-Fi, it could be VLC, or it could be FSO, or it could be all of these which may be which may be implemented in the near future in different applications or use cases. So we discussed about the different applications, and of course the main challenges are still there. Line of sight is a pretty big requirement. And whenever people are also working on hybrid systems, wherein if there is a breakage in the line of sight, then the system would fall back on the RF signals to keep the connectivity alive. So it would be means consider a scenario where I'm trying to download something which is quite a huge file of the order of maybe terabytes. So if I have such a huge file, then when I want to download that thing using present day standards, even if I have 1 Gbps of connectivity, I'll need 1000 seconds. So I'll need to wait quite a lot of time. But if I am able to get an optical wireless connectivity which is able to give me 400 or 600 Gbps of connectivity, then that would 1 TB of data would be possible to download in a few seconds. So if I have a disconnection because of some opaque object in my line of sight, then the RF can keep the connection alive, the download can keep continuing through the RF. So people are working on that also. So there's no solution as of now, to the best of my knowledge, which integrates both these technologies. So maybe it might be possible that AI optimized networks might be able to implement this type of connectivity. And of course, standardization, as I was discussing, for Li-Fi in 2011 there was one standard. So after that, I don't think there are many new standards which have come up, but people are working to make it better. Of course, terahertz communications, that is one aspect which would be covered in another session also. That is a competing technology actually when I look at optical wireless communications, or Li-Fi, VLC, or FSO, could be anything. So terahertz communication may be a better candidate, and we may not be able to see any of these technologies in the near future. Even that is a likelihood. So these are the references. So you would be getting access to all of these materials shortly. So thank you, and if any one of you have further questions. You can raise your hand, or you could probably type it in the chat. If you do not have any questions, we can conclude this session now. You all have my contact information. You can drop a message anytime. and I'll try to answer them. Thank you. Close చేద్దాం.